Presented by Caltech.
So let's do a recap from last night first. Like any good Netflix episode, it's intense. And one day, the next day, we have a nice recap at the start, just like that. So far we discussed damped harmonic motion. A lot of math going on. We discussed the fact that, all right, you have a damping term, gamma z dot, proportional to the speed of the particle in one dimension. This is viscous damping. This is not frictional damping. It's not electromagnetic wave damping, nothing like that. And then what you do, you plug a guess, which we call the ansatz, some exponential form because they are stubborn functions. You differentiate them, they don't change. So there's some hope that this might solve the differential equation up here. You solve a quadratic for alpha, you get two roots, two solutions, as expected. Second order differential equation. Different cases. Is gamma squared more than, less than, equal to 4 omega naught squared? If this is the case for if gamma is less than 2 omega naught, I was calling it underdamped, the book calls it lightly damped, so just two different ways of the same thing. You find the two alphas, alpha is complex, go back to the real plane, you have a damped oscillator whose amplitude keeps on decreasing by an exponential on the law, given by e to the minus gamma t over 2. And there are some oscillations occurring at omega u, which is less than omega naught. And therefore, the time period of this oscillation, which I'm calling t sub u, is less or more than the natural time period. More or less. More or less the same, no? More or less, has to be one way. More, because if the frequency is less, it takes more time to cover one cycle, okay? So t sub u is more than t naught, t naught being the natural time period, 2 pi over omega naught. So it's a real oscillation and it dies off as time goes on. The other case was the overdamped case, where gamma was more than 2 omega naught. In this case, alphas were both real, and we defined quantities mu1 and mu2, which were positive, and we had the relation that mu1 was more than mu2 was more than 0. And therefore, you have two damped solutions, which never oscillate. So in this case, there are no oscillations. And as I was saying to you last time, late time behavior, as time is really, really large, the second piece dominates because mu2 is less than mu1, hence the first piece dies off much more rapidly than the second piece. These things become important very soon, so just keep that in mind. And the third case was when we had critical damping, was when exactly gamma equals 2 omega naught. In this case, alphas are degenerate. They both have the same value, just minus gamma over 2. And the two solutions that we found were either e to the alpha t or t times e to the alpha t. So x as a function of time in the critical case was some constant plus some other constant times t times e to the minus gamma t over 2, and gamma over 2 is omega naught, so this is c1 plus c2t e to the minus omega naught. Okay? And critical damping is important because, as I mentioned last time in the end, again, there are no oscillations here. No oscillations whatsoever. Oscillations only occur in the lightly or the underdamped case. Okay? So, no oscillations here as well. I don't know the spelling of oscillations. But the cool feature of critical damped situations is that if you perturb a system and you leave it, it comes back to the origin the fastest. It takes the least possible amount of time across all these three cases to come back to the equilibrium the fastest. So it has the fastest return to the equilibrium position. And again, I'll repeat myself from last time. This is used everywhere in your everyday lives. Your doors, again, use critical damping. They are not underdamped, they are not overdamped. They are critically damped. Why? Because if it were underdamped, if I open the door, it comes back and it keeps oscillating back and forth and it takes forever to die out. You don't want a door to do that, right? The overdamped case, it will take forever for it to just close once. It takes a while, okay? But in the critical damped case, you open the the door, and as fast as possible, given the configuration, it flows back. Okay? Shock absorbers in cars and in machines, they all use critical damping because any perturbation, any bump, you don't want your car to, go wobbly all the time. You want to absorb the shock as quickly as possible, and hence it's critically damped. Your instruments, for example, things which measure stuff like pointers and things like that, they have a spring mechanism which sends the pointer to the value when you measure something, like a voltage or a current or whatever. It's critically damped again. You want it to stop as fast as possible and not keep oscillating forever or be overdamped. So this thing is important. And I had planned to prove this in class. I do the actual math. Then I thought, how could I make your lives hard? So we will make you do it, just not today. I'm an person. I have that, sorry. So we'll get back to this later on in the course. At some point, you'll see this. So we prove this together someday. All right, so that's the broad idea of how these three different cases work. Any questions about the math, the logic, the physics? Because now we're going to turn to the energy of these things. I know in lecture yesterday and also on Professor Porter's notes, bunch of math, it's all nicely done. We take a slightly different route on the energy, see how we understand it in a slightly different context. But any questions about the construction, about the basic idea? All good? You all see what's happening? Okay, I know this is pretty bland. There's not much going on, at least, thinking-wise. So hopefully you'll pick up soon. One thing I want to mention is that in the underdamped case or the lightly damped case, if it's very, very light damping, so it's very light, and because of which gamma is much, much less than 2 omega naught. There's a damping term, but very small. In that case, how do I approximate omega u? Omega u is up there. I can Taylor expand, I can binomial expand my square root, because gamma is much, much less than 2 omega naught. And therefore, omega u is approximately omega naught times 1 minus 1/2 gamma squared over 4 omega naught squared, plus some terms which are order gamma to the 4th. Okay. So whatever correction comes out further, the next term will have a gamma to the 4th, gamma to the 6th, and so on and so forth. Okay. And if gamma is much, much less than 2 omega naught, all these higher order terms, maybe I should be a little more careful, this will be something over omega naught to the 4th. So this ratio is less than 1. And therefore, it keeps on becoming smaller and smaller as terms go bigger. Hence, I can neglect all of these, all the higher order terms. And what you find is that the underdamped frequency, omega u, is approximately omega naught minus 1 over 8 gamma squared over omega naught squared. And the cool piece here being that for small damping, to linear order, so to leading linear order, omega u is approximately omega naught. The correction that occurs in the first place is order gamma squared. Okay? So if it's gamma over omega naught is small, the correction is going to be pretty small as well. So to linear order, you can always approximate omega u by omega naught. It's all about approximation in this course. At what order do you want to approximate? Your problem in the homework with the catenary, some of you have seen it so far, and you look troubled, concerned, like, oh my god, you guys, don't dial it up. That's hard. And that thing as well, it's all about approximations. How do you think about small motions? Which terms could you neglect? Which do you have to keep? And so on and so forth. So approximations form a big part of physics because not everything is going to be solvable, and we must think about what approximation is good enough for our purposes. So for linear order approximations, there is no change between omega u and omega naught. Okay, energy. So since only the lightly damped case or the underdamped case has oscillations in it, the other two do not oscillate. And the course is about oscillations. we'll focus on the energy of these underdamped solutions. Okay? So the energy, let's first go generically. I think in lectures, Frank basically did a special case where the lightly damped found an equation was nice and good. Let's talk more generally and see what we can learn from broad principles in physics. Okay? So what's the energy of the oscillator, the mechanical energy? It's moving around, has some kinetic energy, so it's 1/2 mx dot squared, and has some potential energy because there's a spring attached to it, it's moving back and forth, plus 1/2 kx squared. Anyone concerned that this doesn't have the friction term in it? Or are we all convinced that the mechanical energy is just this? People often wonder, hey, this was the energy in the case of the non-damped case. Shouldn't there be another term which adds the frictional piece? No. This is the energy of the particle in motion. The damping would be accounted by the x dot and the x. If it were not damped, x and x dot would just be oscillating sines and cosines. But now that they are damped, they also have this exponential envelope, which brings them down. Okay? So energy is just the kinetic plus the potential, and depending on what the solutions are, they exhibit different behavior. Okay? All right, so that's good. This is energy for the underdamped case, only for that. Of course, the same expression holds for overdamped and critical damped as well, but we'll work it out and understand what happens in the underdamped case particularly. But right now, it's all general. Okay. You know what? Let me take the word off for now. I don't want to confuse. This is general for now. This is just for all possible cases. Okay, I have the energy. If you're bored with the energy, what do? Just differentiate with time. Got to pass your time, right? So just differentiate. dE dt. How much is that? Chain rule. 1/2 is a constant, doesn't move. M is a constant, hopefully. X dot squared differentiated is 2x dot, x double dot, plus 1/2 k 2x, x dot. Okay? Simple chain rule. Differentiate with the argument, plus u, and get back to the second derivative, which is particular against. Should I put this to 0? Yes or no? No. Good. Because again, this time energy is not conserved. The frictional forces are damping the situation out and taking energy away from my system as it evolves in time. So this thing is not conserved. Okay, it is not 0. Let's work it out what you get. The 2's cancel off on both pieces. X dot is common. I bring that out. I have m x double dot plus kx. I see some smiles around. Now this piece should look somewhat familiar. Mx double dot minus the force, something like that, right? Now in the particular case where there was no damping, if gamma were 0, what is the bracket piece? 0 is all right. Let's get back into that in a second. I don't think everyone likes these at the moment. We get back. Okay. Look at the equation of motion. Look at the equation of motion again. Just replace z with the x's. That's my real equation. Okay. So z double dot plus gamma z dot plus omega naught z, or x double dot plus gamma x dot plus omega naught squared x equals 0. And what I have here is mx double dot plus kx. And if you remember, it's a little massaged, we can kind of go back. The equation in terms of the masses explicitly written out is mx double dot plus gamma x dot plus k times x equals 0. Is that okay? Okay? Just the harmonic piece, simple harmonic motion, and the damped piece. And I have 2 terms out of 3 and a 0. We got lucky. I can just use this equation and change this into a minus gamma x dot. Okay? So I have dE dt is x dot times minus, actually hold on, this should have been a b. Yeah. my bad. It's a B there. B divided by the mass is a gamma. So that's B. All right, so times B times x dot. Okay. And therefore, the EDT is minus B x dot squared. So the rate of energy loss, is it loss, first of all? Let's verify that. X dot square is always positive. X dot could be negative, but it's squared up, it's positive. B was a positive constant by assumption because it was damping it out. B is positive, this is positive, negative sign. So this whole thing is less than 0. And that should make sense. If there is damping in the system, the energy must decrease with time. I did not use any particular solution, underdamped, overdamped, nothing. I just used the equations of motion and my definition of the energy, and see that the energy will always go down with time. Okay? And now let's go back to this 1A again. Flashback a year. I can write down this dE dt. So it's minus B x dot times x dot. So minus B x dot times x dot. What's minus B x dot? It is the damping force, right? It's the damping force. So this is the damping force, F damp times the velocity. And the rate of change of energy is the power. Ring a bell? dE dt is the power. And we learned back in Phys 1A, hopefully you'll remember, that the power dissipated is the dissipating force, its dot product with the velocity. Okay? The dissipating force with the velocity. It's one-dimensional, so you just get the expression out here. So this is the power dissipated in the damping system that we have here, not considering any particular case, just the generic energetics of the system. And now let's look at the special case. If gamma is 0, that means B is 0, because B is just gamma times m. And therefore, dE dt, energy is considered. Okay? You all see that? All right, sounds good. Okie dokes. Now let's kind of go back to the special case of the lightly damped solutions, or the underdamped. And don't mind me using a different notation in class than the book has. It's kind of deliberate that I do this because the book's notation sometimes is not very, foresight oriented. You can't really see what's going to happen. Using certain things like, these mu's and stuff help you have a handle on the switch a little better, I feel. So try and compare it. If you have any questions, ask me. It's the same thing as in the book, just done slightly differently, I feel. Okay. So the energy again is 1/2 mx dot squared plus 1/2 kx squared. For the lightly damped case, x of t is some amplitude which is dying with time. All of us are. Sorry, that was dark. I had these moments. Okay, so you have the solution. Differentiate, put it back, pull back the x, square, spend a few hours, come out of it, all trouble. Pretty high expression you can. Okay? And I think Professor Potter worked this out in lecture yesterday. I'll just give you the final answer and get you to the main point I want to kind of emphasize today. So what this comes out to be is 1/2, I'll cheat, 1/2 m a squared e to the minus gamma t times gamma squared over 4 cosine 2 omega ut plus gamma omega u over 2 sine 2 omega u plus omega naught squared. Alright, got it. So it looks horrible, but the takeaway point here being that the oscillation of the energy is not happening at the same frequency as the motion itself. The energy is oscillating at twice the frequency, 2 omega u's. So energy for this case is, I don't know the spelling of the word oscillate. Oscillates at frequency 2 omega u. Could someone make sense of this claim? Why is the energy going down or changing at twice the frequency? Not thrice, not 4 times, twice. But the motion itself has the frequency omega u. Any thoughts about that?
The energy dissipated is proportional to the velocity, and the velocity is at its maximum twice per period.
Excellent. So that gets there, but just missing one thing. It's not only about the maximums, right? Even if you're going one way and coming back the other, you're losing energy all the time. While in the motion, you had the right thought in mind. For a simple motion, it's going back and then coming back. But for every cycle, it's losing twice the energy because it doesn't matter if you're going or you're coming back. Dissipation is still dissipation. It keeps on losing energy. And therefore, this twice the frequency is manifestation of that idea that going back and forth, there's a double factor of that. Okay. All right, now for the case of very light underdamping. So when gamma is much, much less than 2 omega naught, in that case, again, to linear order, omega u is approximately omega naught. I can average this out. The average pieces will vanish for the oscillating pieces because they don't change as much for the very lightly damped case. And what you find, you just work it out, is that energy is just 1/2 m omega naught squared a e to the minus gamma t. Okay? I just dropped out these two oscillating pieces. So this is the average energy that I have over time. So I average it out over a few cycles under the assumption, or even one cycle for that matter, under the assumption that omega u is approximately omega naught, there is not much change happening because it's very lightly damped. Energy is falling with time. And this piece here is what the energy would have been had there been no damping, which would have been constant, and it's now dropping with time. So this gives you an interpretation for gamma. Of course, gamma is in the equations, but this tells you that gamma is the rate, like 1 over gamma is the rate at which the energy falls down. Okay? So I think as defined in lecture yesterday as well, we call this tau, which was 1 over gamma. It's like the characteristic time, lifetime. I forget these names, but it tells you a characteristic of how fast the energy drops as you go down. Okay. All with me? Yes, this should be an A square. Thank you. That good? Yeah, okay. All right. And also, just quickly, we also define this thing called the quality factor. So the Q value, which we define as the ratio of the natural frequency over gamma, which tells you, again, just very generically, how does my natural oscillation compare with my damping? Okay, that's it. What dimensions does Q have? Length, mass, time, 5 dimensions. Gotta speak up. I know it's like week 2 is ending, we're all tired and stuff, but come on, we gotta speak. Dimensions. None. Okay, can we all see it, or just the fact that we've been using comparisons and hence you're like, yeah, it's got to be no dimensions. It is no dimensions. But let's just make sure. So omega naught has dimensions of 1 over time. So it's second inverse. So this is second inverse. Gamma, what are the units of gamma? So gamma was B over M. Okay? So I know the dimensions of mass. What about B? Not the most obvious thing. So let's work it out. The damping force was minus B x dot. Okay? The force is newtons. So this is Newton. There's a B x dot. So it's B, whatever dimensions B has, times meters per second. So the dimensions of B are Newton second per meter. Newton is kilogram meter per second square, n times A. So that's Newton. Second over meter, that's my dimensions for B. The m goes away, the s, 1 power goes away. So this is just kg over s. That's B. If I have B, gamma is B over m. So that is kg over kg times second. I'm going back and forth between kgs and masses, but you know what I mean. The kgs go away, so gamma is also inverse second. And plug this back here. And this is dimensionless. I was hoping this would work out. Okay, so it's a dimensionless number. It compares the natural frequency versus the damping. And this is how it looks like. If I have a very lightly damped oscillator, it'll keep on going for a long time. So this is small. This is large Q because omega naught is large. If I have something like this is Q smaller than that, and for a very small Q, small, smaller, smallest. God will learn the hierarchy of things. But what I want to emphasize with this graph is not just that I can draw, but also the fact that as Q is decreasing, the time period of oscillations also increases. Okay? Why? Because omega u, where are you? There you are. It has a ratio of 1 over q squared. So for smaller the q, it takes longer for it to oscillate and dies off also much quicker. Okay? So there's two effects happening here. Not just the fact that it dies off quickly, it also oscillates with a much longer time period. And a quick, if you're an experimentalist, if you ever go and want to measure some resonating cavity, some superconducting junction, or something in nature you want to measure, when you have kids, you're going to put them on swings, you want to measure how much time takes to damp, all that kind of good stuff. Q is also, we can ask the question that, for the case of very light damping, where gamma is much, much less than 2 omega naught, by what fraction does the amplitude fall after Q cycles? It's one question to ask, right? So, after Q cycles, my amplitude is like what fraction of the initial amplitude? Okay, we can ask that question. And how are we on time? We're okay. So, how much time does it take for Q cycles? So for Q cycles, omega u, the frequency of oscillation, times that time will equals 2 pi q. Okay? So for Q cycles, it takes time t connected by this. You all see this? Okay? So the time taken is just 2 pi q over omega u. For the very very light damping case, to linear order, omega u is approximately omega naught. So this is approximately 2 pi over omega naught over q, over gamma. No, sorry, I got this right. Yeah, q. Okay? And what is this? Omega naught over q. Omega naught over q is gamma. So this is 2 pi over gamma. And the final amplitude, A final, is e to the minus gamma t over 2 times A initial. As you can see from the solution up here, amplitude is falling down by the exponential e to the minus gamma t over 2. I put this back here. What do I get? E to the minus gamma over 2 times the time for the Q cycles, which is 2 pi over gamma. The gammas cancel off. This thing is just e to the minus pi, which is about 0.043. It is independent of omega naught. It's independent of gamma. So with a very lightly damped case, what you can do is, if you don't know these values of gamma, you can just start counting the number of cycles and see when the amplitude is 4.3% of the initial one. Count 1, 2, 3, 4, 5, done. It reached 4.3%. After that number of cycles is the value of Q. You have omega naught, find gamma. Okay? Again, approximations are helpful. They tell you like different cases, get a handle on things, approximate them, and you can do it this way. Okay? Any questions about that? Let's take a minute. This is still too hard. I don't want to give it, but take a minute. Just have a look about the energy, energetics in general, amplitudes dropping, the Q factor, whatever comes to mind. It's not a one-way street. We got to talk more. All with me? All right, that's good. Smart kids. That's good. All right. I'm going to fix this down for a while. Okay. Let's quickly do a simple example. So charges, electrons, protons, things like that. It's a known fact in electromagnetic theory, the classical electrodynamics, which all of you did in physics 1B, hopefully. The classic EM. Solve Maxwell's equations. That kind of good stuff. We'll get to that eventually in this course as well. But the point being that if you have a charge and the charge oscillates, if it accelerates in general, the charge radiates energy. Okay? So accelerating charges radiate away. They give off energy as electromagnetic waves, and we'll talk about that. So if a thing is oscillating, it's accelerating, hence it gives off electromagnetic radiation. If it's giving off radiation, radiation has energy, hence the energy of the oscillator is also going down. Okay. So again, if you work it out in classical electromagnetic theory, what you find is that the rate of energy change is some constant, kappa. I'll tell you what that is. Electron charge square. So this is a model for an electron oscillating, okay, with a charge E. When it oscillates, it radiates away, or it loses energy at this rate. E squared, acceleration squared over speed of light v. Okay? This is not viscous damping. This is not friction. This is electromagnetism. Once you compute it, this is what you find. Okay? You won't actually find how you get this, but this is a given to you. All right? At this rate, the energy is falling down. Okay? That kind of starts. I'm too old. We had a whole different set of history. Anyway, so again, if it's oscillating, it will radiate. Why? Because it has acceleration. So think of an atom, think the hydrogen atom. There is the nucleus, the proton, and there's an electron going around it. Again, I'm sure somewhere in the ethereal lands, you know, all the quantum gods like Schrödinger and Bohr, they're like kind of looking down upon me and saying, "You screwed up, man." This is not how the atom works. There's a whole bunch of stuff happening inside the atom. Forgive my demonstration that the electron is an orbit. It's not. There's a whole quantum mechanical mess which happens up here. But for now, again, we are young, we can make mistakes. The electron is orbiting around the nucleus. It's accelerating. There's an A, it'll radiate. Okay. But again, working with circular orbits is hard. I'll approximate this by far away as a simple one-dimensional oscillator. Okay. Electron just going back and forth in one line. I can do that. So if I have an oscillator like that, how does the position change with time? This is a lightly damped oscillator. It'll oscillate but radiate away very slowly. Okay? And for one cycle at least, it's almost like a sine wave. Okay? So for one cycle, roughly, x is like some amplitude times sine omega t. And omega is the frequency at which it moves around. In the atom, it's the frequency of its revolution around the nucleus. If that language even makes sense, it doesn't, but again, we are young. All right? That's my change of position in my approximation of a one-dimensional oscillator. What's A? X over dot minus omega squared x. Simple harmonic motion, right? Differentiate twice, get two factors of omega out with a minus sign. That's what we've been doing so far. Okay? So A is minus omega squared x. I can plug this back here. So the question I ask you is, how much energy is lost in one cycle? What's delta E for one cycle? What do? You have the rate of change. It tells you at every point how are you changing. Keep adding those changes up, get the net change. Okay? So delta E for one cycle is integral kappa E squared A squared over C cubed dt. And t goes from 0 to 1 cycle, hence 2 pi over omega naught. Kappa was a constant. If you want a number, it's 2/3 times 1 by 4 pi epsilon naught. Just depends on the permittivity of free space with a bunch of numbers in it, and pi is just a number. I can pull them out. Kappa is a number, E square is a number, C cube is a number. I have integral A squared dt. A square is omega to the 4th, which is again a constant, comes out. X squared dt. This is kappa E squared omega to the 4th over C cube. A squared from the expression for x times sine squared omega t dt from 0 to 2 pi over omega. Let's call this omega because it's slightly damped. So again, if you linear order, they're the same. You can work this out, get an expression. This is just a number. This integration here. Long live Mathematica. This is pi over omega. I worked it out last night. Plug it in, get a number. Okay. So you found a value for delta E, the energy lost in each cycle. Okay. And once you have delta E, I can go back to my quality factor ideas and find the quality factor for the atom there. So my expression for energy, the way it falls down, average energy is the initial energy times the exponential decay. Right? If it's slightly underdamped, this should be pretty easy to see that delta E over E initial is minus gamma times T. Taylor expansion again. Taylor expand this energy expression out, find the delta E, divided by the original one. This is what you get for one time period. Okay? Now I have delta E. E naught is just 1/2 m omega square A square, energy of the oscillator to start off with, which damps. Fractional change depends on gamma. T is just 2 pi over omega. Delta E found up there. Plug it back in, get the value of gamma. Once you get gamma, the characteristic time, tau, was 1 over gamma. Okay? You can all work it out. It's just a matter of plugging in numbers in again, equations. But the key takeaway here, the physics idea, for let's say an electron oscillating at the frequency of the green color, So about, if the frequency corresponds to a wavelength of about 500 nanometers, that's the frequency of oscillation. The time scale of its decay is 10 to the minus 8 seconds. Now that should worry you. The hydrogen atom is losing energy at a rate 10 to the minus 8 seconds. Bam, we all should be gone. We should not even exist. The universe should not be the way it is. It should just be energy all over the place. So what is preventing these accelerating, orbiting charges to radiate or not radiate and keep the universe stable? If you have your jaws dropped out right now, I will just put them back in. It's next turn. And that's all. So this is quantum mechanics, and next term in Phys 2b we talk about how quantum mechanical ideas save the universe, save the day, by basically not letting atoms radiate away so quickly. So classical electrodynamics predicts this catastrophe in nature, but quantum mechanics is what kind of comes to the rescue. So that's like a cute example that even if you just know how the energy is going down, you can work out the quality factor, work out the time it takes to like change it out, and so on and so forth.
How did you get that ratio between change in energy and equal to
Good.
negative?
So I have this. So this is E naught. So I have E as a function of time is E naught e to the minus gamma t. If gamma is small, this is roughly E naught 1 minus gamma t. What's delta E? Is E minus E naught, which is just minus gamma t. This is minus gamma t divided by E naught is what I have. Thank you. This is gamma t times E. Yeah. Okay, thank you. So just Taylor expansion again. Okay. Now for the last 10 minutes that I have, I want to teach you math. Differential equations. We were told yesterday that you guys are not being taught diff EQs in the way we would like you to be taught, like at least. Do people here know what the homogeneous equation is, the particular solution is? I see some nods. Does everyone know it? We don't need to. That's what I'm here for. They pay me for this stuff. So let me kind of physically motivate a slightly more interesting scenario, which we'll talk about in detail next time, of course. But we do the math, underlying math today. So consider a driven damped harmonic oscillator. So again, you have x double dot plus gamma x dot plus omega naught squared x equals not 0. Now, instead of having the oscillator by itself being damped out, I have someone or some agent or something moving it around externally. There is an external force to the system. So with some amplitude f naught is an oscillating force as well, cosine omega t, and I have a mass division everywhere. I divide the mass out, f naught over time. So I am driving my oscillator, which is damped by an external force f naught cos omega t. Okay. So you might ask, hey dude, usual forces that I drive things around with need not just be cosines. They could be more complicated than that, and they would be. Remember my first class last week, Wednesday, where I tried to convince you that once you have solved for the sines and the cosines, you can put them together like an alphabet to get everything out of it, the Fourier decomposition. So there's a deeper mathematical thing happening. If you can solve for a single cosine, you can all put them together to get arbitrarily complex stuff. So we'll work with a single cosine for now. Okay. So some driven force from the outside. Notice there are two frequencies here. There is the natural frequency, omega naught, and there is the driving frequency, which I'm just calling omega. Omega is what you choose. Omega bears no relationship with omega naught. Omega bears no relationship with omega u for the underdamped case. It is what you choose to move things around with. Okay? You're driving it at this frequency. Now, there'll be a bunch of math next week behind this, physics of this, but let's just think broadly for a second. What is happening? There is a damped oscillator which wants to oscillate by itself at a frequency omega naught. The damping makes it damp out. But now I am adding an external force and making it go around at a different frequency, omega naught. So expect two kinds of behaviors. One would be the transient behavior, and the other would be the steady state behavior. What do I mean by that? The transients, I start off the oscillation. Some initial conditions, it starts oscillating. It's being driven, but it's oscillating. Whatever natural frequency part there is, what we did so far under damped cases, the gamma piece, the damping piece, will make it die out. Remember how the natural oscillations die out in the undamped case? The gamma is damping it out. So in the transients, there will be this die out of the natural frequency, along with adding the external force, which is the transient part as things are evolving. Okay? But after a very, very long time, you sit around, you grow old, get a white beard as a soon about to get, live the life. Once it's all happened in the steady state, my natural oscillations have all died out. What just remains is my driving frequency. So in the transient state, it's a mess. It's a combination of the underdamped case plus my driving piece. They're both playing together. For long times, as t goes to infinity, the natural underdamped piece has died out, and all that remains is the driving piece. So for late times, my driven oscillator is oscillating only at the frequency omega. Out here, it's a combination of omega u and omega. Okay? So in anticipation for next week, we're just looking for, there'll be two kinds of solutions. Transients, when things are evolving, it's a mess, and late times, when the natural pieces are settled out, and the thing oscillates at the driving frequency, omega. Does this physically make sense? Just intuitively, what would happen? Okay? All right, that's great. Let's now learn some math. How do you solve equations like this? We had a zero here before. That was hard enough. Isn't there enough pain in the universe as it is? There should be a law of conservation of pain, you know. D pain, dt should be zero or something. Pain just goes on. Time goes on. Anyways, so how do you solve these things? And mathematicians taught us a way on how to do it. These are called inhomogeneous differential equations. It's like a 10-minute crash course. I don't know how many minutes I have. 5-minute crash course on inhomogeneous differential equations. That's all you need. Come on, let's be honest. So inhomogeneous differential equations. This is math. We're not going to be talking about oscillators anymore for the next 5 minutes. Just math. Think about a variable. And I have a differential equation in the variable y. So y is a function of time, or it's a function of t. I'll be focusing on second order because that's what we need in our course. You could do the same thing for first order, third order, fourth order, my age order, any order. That's fine. So let's think about second order for now. Plus some function p of t, right, times y dot, plus some other function q of t, not the charge, some function times y equals some function q of t. Okay. Most generic second order differential equation. I have a function p of t with the y dot, function q of t with the y, and a driving piece. So in our language, p of t would be gamma, it will be a constant, it won't depend on t. Q of t would be omega naught squared, again time independent, and G of t would be this driving piece. Okay? So this is what our differential equation looks like. We want to solve it. I can start. This is hard. This is not easy. How do you even like go about this? Now here's the beauty of math. I can split this up into two parts. One part is the homogeneous part, where I just put the G of t to 0. Same equation, put G of t to 0. So I have y double dot plus P of t y dot plus Q of t y equals 0. Okay? Don't ask me why. You can just make an equation from this equation by putting the G of t, taking it away. Okay? This is the homogeneous one. Why homogeneous? Because it has a 0 on the right hand side. It is inhomogeneous because it has something non-zero on the right hand side. Okay. Now say that you can solve this. Say you're powerful enough. Mathematica. That's what power is these days. Say you could solve this. And the solution for this is y sub c as a function of time. Okay? This is called the complementary solution. If you can solve for this, y sub c, which solves this differential equation, keep that with you. It's going to come in handy. Okay? Just like in our case, for the damped harmonic motion, non-driven, that's the homogeneous part, this thing, we could solve it. So we have solutions. Okay? We have the complementary solutions, where we have taken away the driving piece. Okay? The second piece is the particular solution, where you keep the inhomogeneous piece, keep the G of t, such that you're saying, okay, there is a solution, y of p, p for particular, ypt, which solves my equation of p. You're like, isn't that the whole point? That's the whole point, where we get to that. So there is a solution which is yp, which solves the inhomogeneous one, yc solves the homogeneous equation. Now I claim that once you've found these two, if I write down y of t as a sum of yct plus ypt, even this solves my inhomogeneous differential equation. Take a minute, convince yourselves. Plug this sum in back here. It's linear, it breaks up. The first piece put in the left-hand side gives you a 0. The second piece put in the equation picks up the right-hand side. So even the sum solves the equation. Okay? So the way to go about it is find the inhomogeneous one. That's the complementary solution. And I'll teach you how to find the particular solution. Find that, plug it back in. Okay? So are we okay staying for 5 more minutes? This is important stuff. I want to kind of finish this off. Thank you. I'm hungry too. I always am. Okay, so how do you find the particular solution? My equation, y double dot plus p of t, y dot plus q of t, y equals g of t. And I'm looking to find yp of t. What do? You guess. That's what you do. That's the mantra behind solving inhomogeneous differential equations. You guess stuff. What you do is look at g of t. Look at it. Just glare. Admire it. Okay? However g of t looks like, try and form a similar solution to yp of t. Now that sounds like hocus pocus. Let's do an example and see how this works. So, example is the best way I actually learned this stuff, I feel. So think about y double dot minus 4y dot minus 12y equals 3 e to the 5t. I can find the homogeneous one. For the right hand side is 0. It looks like a simple damped harmonic oscillator solution which you know. For the particular one, you guess by E of t by looking at the right hand side. Exponential must be an exponential. Some constant a, e to the 5t. I guess this by looking at the right hand side. Okay? And I want to find a now. What do? You plug this back into the equation. What's y double dot? 25. 25 a e to the 5t minus 4. What's y dot? 5a e to the 5t times the 4. It's a 20. 20a e to the 5t minus 12a e to the 5t equals 3 e to the 5t. E to the 5t is shock. Massacre everywhere. All go away. What do I have? 25a minus 20a. That's minus 5. That's 5a minus 12a is minus 7a. So minus 7a is 3. A is minus 3 over 7. Found the value of a. That's you. And you found the particular solution. For this value of a, you got the idea. Okay? We'll do one more quick example and then try and wrap up. Again, the D being look at the g of t piece and guess based on that. So for example, if my equation is y double dot minus 12y dot minus 4y dot minus 12y equals 2t cubed minus t plus 3. First part, homogeneous. Put this to 0, solve. You know how to solve it. Underdamped stuff and everything. The y of p, guess. Now here's the rule. Here's the wisdom of the ages. For an nth order polynomial on the right hand side, guess an nth order polynomial for y of p. Third order. Even though it doesn't have a second order quadratic piece, my y of p should be a generic third order polynomial. So I'm guessing a t cubed plus bt squared plus ct plus d. Okay? Third order. Differentiate, plug it back, and then match order by order. Okay? Once you plug this in, there'll be a bunch of things which you can just map on one by one, right? There'll be multiple equations, solve them together, you get the values of A, B, C, D. Okay? What if my g of t, the right hand side is some, let's say 5 cos omega t or something. Guess y of p by p of t to be A cos omega t plus B sine omega t. Guess that, plug it in, get A and B out of it. Okay? So the wisdom here being, look at g of t. It's an exponential. Keep the same exponential with the same argument, just a different coefficient. Polynomial of nth order, keep the same order polynomial, unknown coefficients all the way down of that order. If there are oscillating functions, keep the same oscillatory function, the same frequency, change the parameters, find them. And this thing has a very imaginative name. It's called the method of undetermined coefficients. Okay, so that's what we do it. So see you guys on Wednesday. We talk about this stuff in more detail with the physics tutorial. Take care.